All right, let's get started then. Our next speaker is Greta Panova, and she'll be telling us that computing symmetric group characters is computationally hard.
Thank you very much. Thank you very much for allowing me to speak here. It's been a while. So this talk is going to be about algebraic combinatorics, very classical one, through the prism of computational complexities, which probably you're not so familiar with, so I will explain, don't worry. But before we do that, let's make sure we are on the same page. We all know permutations, right? So they form the symmetric group, their composition, and we know representations of this symmetric group. As with any finite group, we can do that. So here is one example when we present our group elements as matrices that satisfy the same group law. And what will we do next? We decompose these representations into irreducibles. So I'm actually surprised that this didn't really show up much so far. But here is an example how we decompose this representation into two irreducible modules. And the irreducible representations of the symmetric group are indexed by partitions of n, all of them, give us a complete set of irreducible representations, and in particular a curious fact, which we're not really going to use, but just to mention, is that the dimension of each irreducible representation is given by the Hooke length formula, or the number of standard Young tableaux of this shape, which hopefully all of you know. And how do we study representation theory? If you take an undergraduate class, you're probably going to do characters. So what are the characters? Are just the traces of these matrices over here. And for the irreducible representations, if you pick a basis of these two elements, you can form this matrix, and the character is this permutation is going to be just -1, the trace of this matrix, right? So this is very basic. You should probably all know it, but just to make sure. OK, so why do we do this? So let's go to algebraic combinatorics, and some of the main quantities that show up there, classical ones that we like to study. So some of them, one of the nice examples in algebraic combinatorics are the Littlewood-Richardson coefficients, right? So we take two irreducible representations of the general linear group. These are the Weil modules. We tensor them together. We decompose into irreducibles. We get some coefficients. These are the Littlewood-Richardson coefficients, these multiplicities. They are non-negative integers. What are they equal to? Well, there isn't going to be a formula like the Hooke length formula anymore, but there is a rule, the Littlewood-Richardson rule. We all know it's counting the number of some semi-standard Young tableau with some conditions. Whatever they are, it's not so important. It's important there is a rule, right? So we can, for example, if you want to show that the Littlewood-Richardson coefficient you are working with is non-zero, all you need to do is find one of these tableaus that show that it does the job. What's next? So the next thing we like to study, well, if you take two irreducible representations of the symmetric group and tensor them together and decompose the same way, you get the Kronecker coefficients, which you can also write in terms of the characters of the symmetric group like this. So it's a big sum of products of these characters. And of course, yeah, so everything can be done in terms of characters. And another thing you can do is Platism coefficients. You compose two irreducible representations of the general linear group, decompose that into irreducibles, you get some non-negative integers. What are they equal to? So this is maybe a reference to the Open Problems in Algebraic Combinatorics conference that was a year ago in Minnesota, and maybe many of you were there. So we were talking about these problems, and we're still going to be talking about these problems, and nothing has been solved from those. So of course, what is the main problem? The main problem is to actually find a way to a nice combinatorial formula for the Kronecker and Platism coefficients, just like with the Littlewood-Richardson one. So we already know that the Kronecker coefficients generalize the Littlewood-Richardson. Can we say for them that they count some nice objects? So this is what we call combinatorial interpretation, right? So that's the main question. What is a combinatorial interpretation? In some sense, this is it. So some kind of nice objects that we are counting. So what do we know for the Kronecker? Not much. So I just list here a bunch of results, but they are very, very special cases. And the list hasn't been updating much recently, unfortunately. And the same thing is going to be true for the same question holds for the Platism coefficients. Again, what do they count? We don't know. And one of the reasons that we want to ask these questions, not just because they are natural questions to ask from combinatorialist point of view, but also because these coefficients show up in another area of research, this geometric complexity theory, which is trying to distinguish computational complexity classes. So somehow we are revolving around computational complexity, but let's look at it from another side. How do we define combinatorial interpretation? What is it? So how can we? So suppose that this actually is really impossible in the way we want it. How are we going to show that this problem wouldn't have a solution? Can we do that? So let me propose a plan, but before that I need to explain what computational complexity is about. It's about how fast a problem can be solved with a computer. So when you think of any computer, if you want even your phone, the machine model is not going to be so important here as long as it's classical computer, not quantum. So we have some input, we have some algorithm, we want to get an answer. In the case of decision problems, the answer is going to be yes or no. Is there an object? Is it not? So the input size is how many bits we encode the input, and this is how we are going to measure the complexity. How fast does the fastest algorithm run that can solve this problem? So the class P is the class where the answer can be obtained in polynomial time. Polynomial in n, the class NP. Sorry, and then here are some examples. So actually deciding if an integer is prime, this was a big breakthrough. It actually takes polynomial time. And some other examples. And then the class NP, when you can verify the answer in polynomial time, in the sense that you may not find the object that you're looking for in polynomial time, but if such an object exists, I can give it to you and you can actually check that it's the right object in polynomial time. So for example, one of the essential problems in computational complexity is Hamiltonian cycle in a graph. So you may, all algorithms that we know run in exponential time to find it, but to find if there is one. But if there is one, I can just give you the sequence of vertices and you're gonna check if they are all connected by edges. And of course, well, is P equal to NP? That's the big problem. But for the talk from now on, we are going to assume that they are not equal, because otherwise none of this is going to be interesting. Well, not on. Okay. So then there are the counting problems where, again, we have some input algorithm. We want to know the number of these objects. And so here are the two main classes, Fp, which is the analog of P. The answer shows up in polynomial time. Sharp P, is the class, the counting analog of NP. It's counting over, it's a positive sum over exponentially many objects. This is what this means here, 0, 1 sequences with polynomially many entries of something like this is an indicator function, which is 1 or 0, and we compute this function in polynomial time. So in the graph, you can go over all possible sequence permutations of the vertices and check each one of them. And then counting the Hamiltonian cycles is going to be in sharp P. But what other examples are there? So we are going to use this formalism to try to explain try to formalize a combinatorial interpretation as a notion. So if there is a very nice formula like the Hooke length formula, determinant formula, whatever nice things you actually compute, and then this problem is probably in the class P or FP when we are counting. So for example, counting skew standard Young tableau, Schur functions, things like that. If we have a positive combinatorial interpretation like the Littlewood-Richardson rule, then the problem is naturally in this class sharp P, because here is the example of the Littlewood-Richardson rule. This is a sharp P formula. We're going over all the semi-standard Young tableau. They are not so many, they are exponentially many, but that's fine. I mean, that's allowing us. And then we need to check for each one of them if it's whatever, a ballot sequence and so on, and that takes polynomial time, or maybe even linear if you encode it well enough. And so if we don't have such a formula, well, we probably don't have a combinatorial interpretation. So here, of course, there's this question mark. We don't know about the Kronikers and the Platisms, but what I'm going to tell you now is that another very natural function in algebraic combinatorics, which is the character square, or the absolute value, is not in sharp P. Assuming, of course, P is not equal to NP and some other computational complexity assumptions. Okay, so characters, what are the characters? How do we compute them? You probably all know about the Murnaghan-Nakayama rule, right? So what is the Murnaghan-Nakayama rule? Is telling you that the character of a representation lambda, so at conjugacy class given by alpha, is a sum over this Murnaghan-Nakayama tableau minus 1 to whatever height of this tableau that you calculate. What's the problem with this formula? You have an alternating sum. Can you tell me from this formula if the character is going to be 0? Or non-zero? Well, it's going to be hard because it's not like the Littlewood-Richardson rule. I show you one tableau and you're done. You have to compute all of them and cancel the minuses with the pluses and see what's left in the end. So, okay. So here is the character table of Sn, of S4 in this case. What do we know about the first column? If we sum up the entries in the first column squared, this is n factorial. What is this? This is really RSK, right? So this is the dimensions, is the number of standard Young tableau. This square is just pairs of same shape standard Young tableau. And by RSK, they are in bijection with the permutations, right? We all know this. And so what about another column of this character table? So let's take this one. Again, the character squared evaluated here, this conjugacy class or this permutation is equal to, so this product, depending on, this is something that depends on the cycle structure of permutation, but it's something very explicit. So does this have a combinatorial meaning? Right? So how do we start? First, we need to figure out if this thing is counting something at all. Like, what is the character square? Is this some nice set of objects? And then we can try to see beyond that. So in order to figure out, does this count something, we ask the quintessential question, does it have a combinatorial interpretation? Or in our paradigm, we formulate it as a computational complexity question. Compute, this is the counting problem compute the value of this character given the input partitions lambda and alpha. And the punchline is that this is not going to be in sharp P, and there is paradigm, there is not going to be a combinatorial interpretation for the character square. So if you actually take the Murnaghan-Nakayama rule, square this, and have all these pairs of tableau, you're not going to be able to efficiently figure out how to cancel the signs. How do we prove this? So I'm not going to use the Murnaghan-Nakayama rule, though I explained it. So I'm going to use a different formula and to evaluate the characters. So we're going to go into set partitions. So what is this set partition problem? It's one of these computational complexity classical hard problems. You have a bunch of items. So this vector A of values is items. These are integers, let's say positive integers to not have any issues. And we have bins of sizes B. And this ordered set partition is going to be the way of partitioning these items into bins such that the sum of the items in each bin is given by whatever this B is. Okay, so this is kind of funny notation here. This is the usual set partition, like Stirling number type of thing, but you have the condition that the item sizes or weights in each bin should add up to this B, right? So these are the parameters, and this actually, if you want to count this, is going to be hard. So of course, Stirling numbers have a recursion for them, but once you start varying this thing, whatever is happening, then this becomes a hard problem. So here is an example. We can pair the 2 and the 7 in a bin of size 9, and then the 4 and the 5 in another bin of size 9, and you can do this in two different ways because this is ordered set partitions. And now we can actually write the character using this Jacobi-Trudy or Frobenius formula as an alternating sum over, so this is going over all permutations of, so K is going to be the length of the partition lambda, and the sign of the permutation, and then we have, for each one of them, we are distributing the alphas in bins of these sizes. So this is just vector-wise, this is the identity permutation, sigma, and lambda, we make a vector of bin sizes. And what we can actually do is we can manipulate this lambda and alpha so that for any, it looks a little bit funny, but for any two integer sequences, C and D, whose sizes add up like this, we can make a character, lambda and alpha, and it's actually linear in terms of this C and D with some number theoretic constraints, so that most of these terms vanish. In the end, we are going to be left with the difference of two ordered set partition problems, which are the same items distributed in slightly different bin sizes. Okay, so what do we do with this? We go from set partition problem into a 3D matching problem. So what this is telling us is that if we take two 3D matching problem instances completely independent of each other, we can find these C and D sequences as before, so that the difference of the number of 3D matching is proportional to the difference of this ordered set partition, in particular the character. How do we do this? So here are our three-dimensional matching. So three-dimensional matching, we have just vertices, and we want to separate them into sets of 3 each. And we are allowed to use those sets. So this is just like normal matching in graphs, except that these graphs, the edges now are sets of size 3, hyperedges. So here are two of those matchings, and we do this. And we put them together as a 4D matching. We encode this in the hyperedges can be written down as quadruples of these vertices. And we can encode each of this as a vector and then as an actual number. And then, so we do this with the vertices as well. Hyperedges, some kind of encoding, and then our matching problem becomes an actual set partition problem. So if we find the matching if and only if we can solve a set partition. And yeah.
Just while you got it out, can you say how you put them into the 4D matching, those 3D matching?
So we add an extra vertex on top, on this side for both of them. And the light gray, these are extended, so XX, so this vertex and this vertex get matched, and the other one gets matched a little bit off.
Oh, okay.
And the idea is exactly that this off matching will make sure that we are either selecting the gray one or the other one when we solve the set partition problem. So this slight misalignment is gonna help us do exactly this difference in the set partition problem. And since I'm out of time, how do we put this together for the computational complexity result? Well, 3D matching is a quintessential hard problem, so Sharp-P complete problem. So what we just showed is that the character is proportional to the difference of two independent hard problems, and this is way too powerful in some sense. So we cannot, so the character, if the character is character equal to 0, this is something called C equals P complete. It's a solution of two Sharp-P problems, whether they are equal. And this is, basically the gist is that this is really hard problem, and this is beyond our characterization. So if the character square is in Sharp-P as a function, then deciding if it's positive is gonna be in NP, right? So there you can show an object that exists there. And the character equals 0 then is going to be in co-NP, basically by definition, it's another class. And by this chain of reasoning, then this C equals P is going to be inside co-NP, which causes the whole polynomial hierarchy in computational complexity to collapse. And this is kind of similar to P equals NP, but at a little bit higher level. And that's basically how these things work. So there's some black box machinery in computational complexity. And thank you very much.
Thank you, Greta. Maybe we have time for one quick question. Over there.
Could you say a little bit about if there are promising targets for reductions from this, like other problems that you can reduce this to? Can you repeat that?
Can I tell if there are other problems we can reduce this to?
Implications from this hardness result.
Implications. Not immediately, but there are other problems related. So there is a problem which I'm always confused about: the sum of a row or columns in the character table. So without any weights, that turns out to be one case is easy, has a combinatorial interpretation, the other does not. So that's maybe one of the first things one can try to do using this, but. We cannot conclude anything yet about the other problems that I mentioned because they are still sums of many characters, and these are big sums of many different characters, and we cannot isolate what's going on to make this kind of like artificial isolation and reduction yet.
All right. If there are any further questions, then maybe we can save them for afterwards. But let's thank Greta again.